Okay, so you know how you always send in the coolest stuff for us to take a deep dive into?
Yeah.
Well, this latest research you sent over is honestly pretty mind-blowing.
Yeah, I thought it was pretty interesting.
Yeah, so it's all about this thing called radiative cooling.
Radiative cooling.
Yeah, and it's like this potential solution for, the whole global warming problem.
Big problem, yeah.
Yeah, exactly. And it's basically like, imagine, surfaces that are like specially designed to cool themselves down.
Buildings and stuff.
Yeah, like buildings and stuff.
Right.
And by cooling themselves down, they actually cool down the planet.
That would be pretty wild.
I know, right? It's like straight out of sci-fi or something.
Yeah, so how do they do that?
Well, that's what we're going to find out today.
Yeah.
So the study you sent is called The Global Warming Potential of Geoengineering via Radiative Cooling.
It's a mouthful.
Yeah, it is a mouthful, but it's a really cool study. And basically what we're going to do today is like really try to understand what it's saying about how effective these radiative cooling materials could actually be.
Right.
And the study actually goes into, different types of radiative cooling materials, and it compares them to like everyday things.
Oh, interesting.
Like stuff we see around us.
All right.
And even like natural surfaces like oceans and forests.
Oh, wow.
Yeah. It's pretty comprehensive.
Okay.
But before we get into all that, I think it's important to remember, like, the context of this whole thing, right?
Sure.
So, like, the IPCC has already reported that the Earth has warmed by, like, 1 degree Celsius.
Right.
And that's because of all the, the stuff we're doing.
Our fault.
Yeah, basically. And what's even crazier is that, like, current trends suggest we could be hitting like 1.5 degrees Celsius increase like between 2030 and 2050.
Yeah, that's coming up quick.
I know, it's like right around the corner. I know, and one of the key ways scientists track this whole thing is by looking at something called radiative forcing.
Okay.
And basically it's like the imbalance between how much energy is coming into the Earth system and how much energy is going out.
Makes sense.
Yeah, so the big question here is like, can we actually engineer these materials, these radiative cooling materials, to like nudge that balance, back towards cooler temperatures?
Could we like hack the planet a little bit?
Yeah, kind of. It's like a hack for the planet.
Pretty cool.
I know. So how does this radiative cooling actually work?
Well, it all starts with the sun.
Yeah.
The sun is sending a ton of energy our way constantly.
It's like a giant heater in space.
It's a giant heater in space, yeah. And at the top of the atmosphere, each square meter is getting hit with about 340 watts of energy.
340 watts?
Yeah, 340 watts per square meter.
Okay.
Now, not all of that makes it to the surface of the Earth.
Right.
A lot of it gets absorbed and scattered by the atmosphere, but around 186 watts per square meter actually reaches the surface.
Okay.
And so the ground and the oceans, they absorb some of this.
Right.
So about 163 watts per square meter gets absorbed, and then a little bit gets reflected back, about 23 watts per square meter.
Makes sense.
So basically, the Earth's surface is soaking up a lot of heat from the sun.
It's like a giant sponge.
It is like a giant sponge for heat.
Yeah. And then I guess like anything warm, it radiates that heat back out, right?
Exactly. You got it.
Okay.
So the Earth's surface, it emits infrared radiation, which is just a fancy way of saying heat.
Okay.
And it's really good at this, actually.
Okay.
We say it has a high emissivity.
High emissivity.
Yeah, so it's shooting out about 240 watts per square meter of heat back up into the atmosphere.
Okay, now hold on a sec.
Yeah.
You said 163 watts per square meter gets absorbed.
Yeah.
But 240 watts per square meter is being emitted.
At the top of the atmosphere, yeah.
At the top of the atmosphere.
Yeah.
So where's that extra heat coming from?
Well, it's not exactly extra heat. So that 240 watts per square meter at the top of the atmosphere, that includes heat coming from the surface and heat coming from the atmosphere itself.
Oh, okay.
So it's not all coming directly from the surface.
Gotcha.
And when you look at the whole system, there's actually a slight imbalance.
Okay.
Right now, it's about 0.6 watts per square meter more coming in than going out.
And that's what's causing the planet to warm up.
That's what's causing global warming.
Okay. So where do these radiative cooling materials come into play?
Well, they're designed to basically tip the scales in the other direction.
Okay.
We want more heat going out than coming in.
Okay.
And so the study talks about this thing called net cooling power.
Net cooling power.
Yeah. And it's basically the difference between how much heat a material radiates away and how much heat it absorbs from the sun and from like the surrounding air.
Okay.
And we want that difference to be positive.
So more heat going out than coming in.
Exactly.
Okay.
And it's measured in watts per square meter.
Okay.
And the higher the number, the better the material is at cooling.
So the higher the net cooling power, the better?
Exactly.
Okay, so how do they make materials with high net cooling power?
Okay, so there are two main things.
Yeah.
First, they need to have high solar reflectance.
Solar reflectance.
Yeah, which is also known as albedo.
Albedo, okay.
Yeah, have you ever noticed how wearing a white shirt on a hot day keeps you cooler?
Yeah?
That's because white reflects sunlight.
Right.
These materials are kind of like that.
Okay.
They reflect most of the sunlight that hits them so they don't heat up as much.
Makes sense.
And then the second thing they need is high long-wave infrared emissivity.
Long-wave infrared emissivity.
It's a mouthful,
Yeah.
I know.
Okay.
But basically it means they're really good at releasing heat as infrared radiation.
Okay.
Now here's where it gets really cool.
Freaking cooler.
There's this special window in our atmosphere.
A window?
Yeah, like a transparent window for heat.
Okay.
And it's between about 8 and 13 micrometers in wavelength.
Okay.
And this is where the long-wave infrared radiation can escape into space
Yeah.
without getting trapped by greenhouse gases.
So it's like a shortcut for heat to escape the planet.
Exactly. And these radiative cooling materials are designed to specifically target that escape route.
That's amazing.
Yeah, pretty neat.
Okay, so this radiative cooling thing is different from some of the other ideas for tackling global warming, right?
Yeah, definitely.
Okay.
So you've probably heard of solar radiation management.
SRM?
Yeah, SRM, which is basically like trying to reflect sunlight back into space, maybe by like putting aerosols into the atmosphere.
Right.
But the problem with SRM is that it doesn't really address the root cause of global warming, which is, all the greenhouse gases we're pumping into the atmosphere.
Yeah, we're still polluting like crazy.
Exactly. And if we were to suddenly stop doing SRM,
Yeah.
temperatures could spike back up really quickly.
Oh, that's not good.
Not good. Yeah. And then there's carbon dioxide removal.
CDR.
CDR, which is all about taking CO2 out of the atmosphere.
Right.
Which is great in theory, but it's really hard to do on a large scale. And it can be very expensive.
Yeah, that makes sense.
So radiative cooling is kind of like this middle ground.
Okay.
It's a lot more energy efficient, and it doesn't have the same risks as SRM.
So it's like a gentler approach.
Yeah, you could say that.
Okay, so we've covered the basics of radiative cooling.
Yeah.
Now let's get to like the really interesting part of the study.
Okay.
They talk about the potential impact of covering just 1% of the Earth's surface with these radiative cooling materials.
Just 1%.
Yeah, just 1%.
That's tiny.
I know, right? It seems like such a small amount, but they found some pretty amazing results.
Okay, I'm intrigued.
Yeah, so to understand those results, we need to talk about this thing called global warming potential.
GWP?
Yeah, GWP, and it's basically a way to compare how much different greenhouse gases contribute to warming.
Compared to CO2.
Yeah, compared to CO2 over a certain period of time, usually like 100 years. And the cool thing is that the study shows you can actually calculate a GWP for these radiative cooling structures.
Really?
Yeah, and because they're cooling things down, their GWP can actually be negative.
Negative.
Yeah, negative.
Yeah.
Which means they can actually offset the warming effects of CO2.
So it's like they're canceling out some of the CO2.
Yeah, exactly.
That's pretty wild.
I know, right? So to figure out like what would happen if we covered 1% of the Earth with these materials, they looked at the average albedo and long-wave infrared emissivity of different materials.
Okay.
And they have this really helpful table in the study.
Okay.
Table 1.
Table 1.
Yeah, and it lists all the different materials they looked at.
Like what kind of materials?
Like everything from these super high-tech radiative cooling materials to like, regular building material.
That's interesting.
Yeah, and even natural surfaces.
Okay, cool.
And they measured how good each material was at reflecting sunlight and emitting infrared radiation.
Okay, so let's get to the good stuff. What did they find?
Okay, so first they looked at this like hypothetical perfect radiative cooling material.
Okay.
Like the ultimate cooling material.
So like in a perfect world.
Yeah, exactly. And this material would reflect all sunlight and emit all of its heat in that special infrared window we talked about.
So it would be like the ultimate heat sink.
Yeah, exactly. And they calculated that this material would have a cooling power of like 165 watts per square meter.
165.
Yeah, 165, and if just 1% of the Earth was covered in this material.
Just 1%.
Yeah, it could reduce radiative forcing by about 1.05 watts per square meter.
Wow, so even a small amount of this perfect material could make a big difference.
Yeah, exactly.
It's pretty crazy.
Okay, so that's the ideal, but what about real materials?
Well, that's where it gets really exciting.
Okay, tell me more.
So the study highlights a bunch of radiative cooling materials that scientists have already developed.
Real materials.
Real materials, yeah. And they mentioned some specific research groups that have created materials with like really impressive cooling powers. Okay, how impressive are we talking?
Like one of them reached almost 161 watts per square meter.
Wow.
Yeah, and another got to around 155, and another was close to 148.
So they're getting pretty close to that ideal material.
I know, right? It's amazing. And if you covered just 1% of the Earth with these real materials,
Yeah.
the reduction in radiative forcing could be almost as good as with that perfect material.
So we're actually getting pretty close to making this stuff a reality.
Yeah, exactly. It's like not just some sci-fi dream anymore.
That's really cool.
I know, right? Okay, so we've talked about these super advanced materials.
Yeah.
But what about the stuff we use every day?
Like what?
Like, building materials, like for roofs and roads.
Okay, yeah, good question.
So they looked at those too, and it turns out that white cement paste is actually pretty good at radiative cooling.
White cement paste.
Yeah, like the stuff they use for sidewalks and stuff.
Okay.
And it has a cooling power of about 98.5 watts per square meter.
Okay, that's not bad.
Yeah, it's not bad at all, and it even has a negative global warming potential over 100 years.
So it's actually helping to cool things down.
Yeah, and if 1% of the Earth was covered in white cement paste,
Yeah.
it could actually contribute to a little bit of global cooling.
Wow. So just by changing the color of our sidewalks and buildings?
Yeah, it's pretty crazy, right?
That's pretty amazing.
It makes you think about all the choices we make when we build things.
Yeah, for sure.
Okay, but what about other materials that aren't so reflective?
Like what?
Like roofing shingles.
Oh, yeah, most roofs are pretty dark.
Yeah, and it turns out they're not so good for radiative cooling.
What do you mean?
They actually have a positive global warming potential.
So they're making things worse.
Yeah, and if you covered 1% of the Earth with roofing shingles,
Yeah.
radiative forcing could actually go up.
Oh, wow. That's kind of scary.
Yeah, it's kind of a bummer because it means that something so common
Yeah.
could actually be making global warming worse.
Yeah, that's not good.
And it's not just roofing shingles.
What else?
Like road asphalt and regular concrete also showed a potential for increasing radiative forcing.
Okay, so we really need to think carefully about the materials we're using.
Exactly. Okay, so we've talked about man-made materials.
Yeah.
But what about natural surfaces?
Like trees and oceans?
Yeah, exactly.
Yeah.
So they looked at those two, and oceans are kind of interesting.
What about them?
So if you hypothetically replaced 1% of the Earth's surface with ocean,
Okay.
it could actually increase radiative forcing a little bit.
Really? Why is that?
Well, it has to do with sea ice.
Sea ice.
Yeah, so sea ice is super reflective.
Okay.
Way more reflective than open ocean.
Right.
And so when sea ice melts,
Yeah.
you get more open ocean, which is darker and absorbs more heat.
So we're losing that reflective surface.
Exactly.
Not good.
Not good at all. And forests actually showed a slight cooling effect.
Okay, so we need to protect our forests.
Yes, definitely.
Okay, what about something like a perfect black surface?
Like if the Earth was just a giant black ball.
Yeah, like,
Well, even though a black surface would be really good at emitting heat,
right.
it would also absorb like all of the sunlight hitting it.
Yeah, because black absorbs everything.
Exactly. And so it would end up having a really high global warming potential.
So it would actually make the planet hotter.
Yeah, so it's not enough to just be good at emitting heat.
You also need to be good at reflecting sunlight.
Yeah, you need both.
It's like a balancing act.
Exactly. Okay, so this study had some pretty big findings.
Yeah, it did.
But how do we know if we can trust it?
Good question.
Did they compare their results to other research that's been done?
Yeah, they did actually.
Okay.
They looked at a bunch of other studies, and their calculations for radiative forcing lined up pretty well with what other researchers have found.
Okay, so it's not just like a one-off study.
Exactly. It seems like there's a growing body of evidence supporting this whole radiative cooling thing.
That's good to hear. Okay, so are there any like limitations to this study or things we should be aware of?
Yeah, there are a couple things. So one thing is that they mostly measured how reflective and emissive materials were when light or heat was hitting them straight on.
Okay.
But in the real world, sunlight hits surfaces at all sorts of angles.
Right.
And heat can be emitted in different directions too.
It's more complex than just a straight-on measurement.
Exactly. And they acknowledge that in the study, and they say that future research could definitely refine these models.
Okay, makes sense.
Yeah.
So big picture, is radiative cooling like the solution to climate change?
Well, it's not a silver bullet.
Okay.
It's not going to magically fix everything,
Right.
especially if we don't also address the root cause of the problem, which is that we're still emitting way too many greenhouse gases.
Yeah, we can't just keep polluting and expect radiative cooling to save us.
Exactly. But it could be a really valuable tool to buy us some time.
Buy us some time.
Yeah. because a lot of the CO2 that's already in the atmosphere is going to stay there for a long time.
Right.
So radiative cooling could help to lessen the impacts of global warming while we transition to cleaner energy and develop better ways to capture carbon.
So it's like a temporary fix while we work on the long-term solutions.
Yeah, you could think of it that way.
Okay, that makes sense.
There's also another thing to consider.
What's that?
So these radiative cooling materials are really good at cooling things down.
Right.
But that might not always be what we want.
Like when it's already cold outside.
Exactly, like in the winter.
Okay. Yeah.
If we have too much radiative cooling, it can make things too cold, and then we'd have to use more energy to heat our buildings.
Well, that would kind of defeat the purpose.
Yeah, exactly. So they suggest looking into something called dynamic thermal regulation.
Dynamic thermal regulation.
Yeah, and it's basically using materials that can change their properties based on the temperature.
So they can cool things down when it's hot and keep things warm when it's cold.
That's the idea.
That's pretty smart.
Yeah, it's pretty cool technology.
Okay, so to wrap things up, what's the main takeaway from all of this?
For me, the biggest takeaway is that radiative cooling has huge potential to help us fight global warming.
Yeah.
Especially these new advanced materials that they're developing.
Right.
It's amazing to think that covering just 1% of the Earth's surface with these materials could make a real difference.
Yeah, it's pretty mind-blowing.
And it really makes you think about the materials we use for everything.
Yeah, like we were talking about with the roofing shingles.
Exactly. It's crazy to think that something so common could actually be making global warming worse.
What do we do now?
Well, I think the next step is to figure out how to scale up the production of these advanced materials.
Okay.
And we need to make sure we can do it in a way that's affordable.
Right.
And then we need to figure out the best places to use these materials.
Like where they would have the biggest impact.
Exactly. Like maybe in cities where it gets really hot in the summer.
Yeah, that makes sense.
And of course, we need more research to make sure these materials are durable and long-lasting in the real world.
Yeah, they need to be able to stand up to the elements.
Exactly.
But overall, this whole radiative cooling thing seems super promising.
Yeah, it's definitely an exciting area of research. And this study you sent is a really good example of the amazing progress they're making.
Absolutely. Okay, so what are the big questions we should be thinking about now?
Well, I think one big question is, how do we integrate radiative cooling into our overall climate strategy?
Right, because it's not a standalone solution.
Exactly. It needs to be part of a bigger plan.
Okay.
And another question is, how do we get people excited about this technology?
Because it's kind of hard to get people excited about roofs and sidewalks.
Yeah, but it's important.
It is important.
We need to make sure people understand the impact that these materials can have.
Yeah, we need to spread the word.
Absolutely. And I think this study is a great place to start.
Yeah, it's a really fascinating look at the potential of radiative cooling.
And it definitely gives me hope for the future.
Me too. So what do you say we end this deep dive on that hopeful note?
Sounds good to me.
All right, until next time.
See you.
Bye. Bye.